I would just welcome all of our viewers. Thank you very much for joining us. And first, I would like to thank you, our sponsor, EIS, for allowing us to use this platform free of charge. And also, please make sure to check our new website. You can see probably, no, on this side of me, on whichever side of me, you can see the new logo. So yeah, we have all the things that you liked about the website before. So information about the seminars, webinars, teaching resources, and coffee breaks. But right now we gave it a little bit, well, newer look. So yes, please make sure to check it. Now about our speaker of today. So this is Stéphane Baudin. He has completed his undergraduate in Strasbourg in France and his PhD in Neuchâtel in Switzerland. And since 2015, he's associate professor for sedimentary geology at Aarhus University. And he specializes in neritic and shallow water carbonates, and he's a big fan of ocean and occurrence. Now, his today talk is titled Late Early Jurassic Environmental Perturbation, a Shallow Water Perspective. And as I know Stéphane personally, and I know that he's extremely good field geologist, I expect to see really a lot of nice field pictures as the ones on the title slide. So yeah, Stéphane, whenever you're ready, please.
Oh, thank you for inviting me to give this talk, and really thank you a lot for all the SEDS Online people and Stephen for this great initiative. And so today I would like to talk a bit about what we are doing now since 2008 or 2007 is the first time I went to Morocco to look at the Toarcian. And I'm giving the talk, but François-Nicolas Krenker, who was my PhD back when I was in Bochum and who's now doing a postdoc with me as well, could give this talk in the very same way. And a lot of the ideas that I'm showing here are actually some of his ideas he initially had and stuff like that. So he's really one of the main driving factors here in this study. And indeed, it's not just the two of us, but we have, oops, is it working? Yep. There you go. We have a lot of people collaborating on this project, PhD students, MST students, postdocs, and other collaborators. They too few to name them, and I hope that I did put the name of every of those that have ever worked with me on that here. And if not, really apologize to those that I have forgotten. So what I would like to talk about here is a bit the shallow water perspective on past global environmental changes. And we know that climate change can affect this neritic environment. So these neritics are these benthic, shallow marine benthic environments, right? But we also know that this can give some feedback, either negative or positive feedback, to enhance or to dampen the climate change as well. So it's also very important to understand what's going on in the neritic environment during this time of climatic upheaval. And plus, on the other side is that there are some information that are locked in the neritic environment that are very important to understand the effect of this climate change that you can more difficultly understand from deeper water sections. For instance, sea level fluctuations, right? Neritic environments are the best place to study that. And they're also very important because they're highly sensitive actually to environmental perturbation, and I often like to see them as the canary in the coal mine for environmental perturbation. They will often be impacted before actually you could see any change in deeper water environments. So they clearly are very helping us to understand global environmental change in the past. And of course, we do this study because we know as well, I mean, we look at neritic environment in the past and how they have reacted to this climatic upheaval, because we have this dire forecast that due to the current anthropogenic perturbation, actually the reefs are at risk, right? And we could, if that goes really crazy, we could actually lose them, right? And they are a very important ecosystem actually for marine environment. So today I would like to bring you to the Jurassic, and to be a bit more specific, to the late early Jurassic. So it's actually the Pliens-Bakken Toarcian transition. So that did occur around 148 million years ago. And what happened at that time is there was this, as you can see here from this curve, there was this large, so negative excursion in the oxygen isotopes that you can record all in all the place basically where we have done these measures, and that is really a big hallmark for a very large warming event that did span this this transition, and it was accompanied as well by perturbation in the carbon cycle. And it is famous this for one oceanic anoxic event, which is the so-called the Toarcian oceanic anoxic event, that is best exemplified here in this in northern England by the so-called jet rock. So these black shales here, you see this very black deposits here. So deep water, relatively deep water, rich in organic matter, black shale, right? And it's the study actually of this black shale that kick-started this whole study about the early Toarcian perturbation, climatic perturbation. With studying piling on, we have started to realize that actually it's not just one event, but it's actually two separated events that are inscribed within a broader, more protracted perturbation. And more specifically, there is actually one first event of warming that occurs around the Pliens-Bakken Toarcian boundary itself, and then a second event which culminate here in the climax of this this whole early Toarcian perturbation, which is then represented by the so-called Toarcian oceanic anoxic event, right? And there are multiple studies that shows that those are really two separated events. So there are two extinction event levels. There are a lot of things going on here, and we think that the culprit here is the eruption of the Karoo-Ferrar large igneous province here at that time. So which this large igneous province had a pulse kind of activity, and it turns out that every time there was a pulse of this large igneous province, there was an environmental perturbation here, culminating at the end in the TOE, right? But all of these informations are coming from more relatively, let's say, deeper water sections, right? And if we turn and look at the Neritic environment, well, the first thing we can see is that actually that's this very nice compilation here from Pflug and Kissling, is that it also coincides with the first order reef crisis. So we are losing during this event 99% of the reefs actually, if you look at reefs, number of occurrence of reefs in different basins per million year actually. So it's a very drastic event. It's one of the major event in terms of reefs, reef perturbation, right? And often, if you go to a section and you want to look at this shallow water section, you want to look at this Pliens-Bakken Toarcian transition, what you would see is something like that. So that's a section in southeastern France, Castres section. I was lucky to do some fieldwork there last year in July, and I thank Philippe Leonid to have guided us there. And so what you see here, so that's an overturned section. So the oldest rocks are here on the top. And here this red line highlights the Pliens-Bakken Toarcian boundary. And then immediately on top, what you have is a middle Toarcian deposit. So that means that there is here a huge hiatus associated with that. And that is really often what you observe in this Neritic environment. It's actually hiatus, right? Here are another example from southeastern France. So here it's a bit more complete, but there is a big hiatus. There are unconformities, a lot of unconformities associated with that, so hard ground and all this kind of stuff. So it's more remarkable by the fact that there is missing sediments than anything else, which makes it very difficult to study actually. The other difficulties with Neritic environment is that quite often the dating is not as optimal as you would like it to be, and this is for example this this study here, Trecali et al. from Italy, where I mean, with the help of carbon isotopes, you can pinpoint and see this negative carbon isotope excursion that is associated with the TOE. And so you could highlight and suggest that here this transition from these two different types of carbonates are actually linked to the TOE, but still It is just the carbon isotopes, and there are some doubts. I mean, although here it's okay, but then this one here was associated to the Pliensbachen Toarcian boundary, but here it's less certain, right? And so a bit to answer that, I'm going here to show you some what we have done in Morocco, actually. And the research question I would like to answer here is, what are the details about the timing and the modality of Neritic carbonate factory change, if any, across these events here? And what are the precise link to the global environmental change? And what factors, both regional and on the global scale, can explain the Neritic carbonate factory demise? Yeah, so there are different factors that can explain that. And so I would like to bring you to the High Atlas mountain in Morocco. And the reason, and I will show you why. I mean, first of all, it's a very beautiful country, Morocco, but then there are also some very good geological reasons to do that. And first of all, let me introduce you to where Morocco, where it was during the Jurassic. So it was in the northern part of Gondwana, as it is nowadays, right? But it was situated at the western end of the Tethys Ocean. There was yet, during the Toarcian, probably no connection towards the Pacific Ocean. And I would like today to go to to show you results from the central High Atlas mountain here, which was this basin here that was open to the east towards the Tethys region, but that was closed on the western side and the northern side and the southern side by the by continents, right? And I will show you mostly results from the southern part of it, and a bit also from the north, but we have we have restrained ourselves to look at what is going on here, mostly in this part of the basin, because there is a lot of salt tectonism that might actually interfere with what we're looking for, which is more a global signal. But at the end, it turns out that it's probably not. And the reason why Morocco is the High Atlas is really great for that is that there is high subsidence rates and high sediment supply here. And this allows us to maximize the potential to record these events that are often otherwise not recorded at all in shallow marine environments. And on top of that, we have outstanding outcrop conditions and lateral continuity. So we can actually walk around surfaces and track surfaces from shallow water to deep water, actually. So we're really able to have a very good constraint on that. We do also have good biostratigraphic control, which is a very important point because we really want to look at the effect of short-term climatic events on that. And so we really need to be able to pinpoint exactly where we are in the chronostratigraphy part. And we do that by mixing biostratigraphy and chemostratigraphy. And for biostratigraphy, well, we use ammonites, nanofossils as well. A lot of work done by Emanuela Mattioli. So that's where we are more in deeper water environment. And when we're in shallow water environment, we're very lucky that at the time in the early Jurassic, their brachiopods are actually very good for biostratigraphy, actually. And they can be as effective as ammonites, actually. So it's we can really pinpoint things at a high accuracy in terms of biostratigraphy. And on top of that, we do chemostratigraphy mostly on so carbon isotopes on the organic matter. And there, for instance, you can see this very large negative carbon isotope excursion. That is the negative excursion of the Toarcian oceanic anoxic event. And this is confirmed by brachiopod biostratigraphy. And so we can really pinpoint to a very high precision level where we are. And, and using then chemostratigraphy as well, we can extend that even to places where we do not have good biostratigraphic control in the basin. And we can, there is no example here shown here, but we have also sections that we have logged in continental deposits and where we are able still to recognize the negative carbon isotope excursion of the Toarcian oceanic anoxic event. So we can really go from the continent to the deep water and have a very high resolution chronostratigraphic framework. And so when we do that, we can actually see that around this transition from the Pliensbachen to the Toarcian, we have a complex transition in terms of Neritic carbonate factory here that I will show a bit more now into details here. And if we start in the Pliensbachen is known for this creature here, which are called liquits. So those were large bivalves. Some people are postulating that they were actually living in symbiosis with photosynthetic algae, right? So with zooxanthellae, so they might have been doing living like I mean corals nowadays, right? So they're very large, and they can be so large actually and so big that they can form entire reefs. And if you see this strange pattern here that looks like fractures, it is actually not. Those are large liquid bivalves that are stacked one behind each other and forming these reefs. So that's François Nicolas for scale here. And those were the ones that were really making the reefs in the shallower water environment around the lagoonal and very shallow water environment. Corals were there as well, but in the Jurassic, and that's a very, very interesting compared to last week discussion about is the present the key to the past. There are a lot of coral reefs in the Jurassic, or at least in the early and middle Jurassic. For sure, they are actually not in shallow water, but they were mostly situated in shore phase to the offshore transition coral buildups. So actually, these coral buildups here, you can, if you go around, you have these nicely bedded limestone beds here, where you have ammonites and belemnites and things like that, for instance. And at that time, the climate in the Plains Basin was actually an arid climate. And we know that we have several indicators, and maybe the most striking one are those Evaporites deposits that we can find every now and then here in the basin. Very nicely bedded Evaporite deposits. And you can see actually that some of them are actually binded by stromatolitic mats, right? In terms of platform architecture, well, there was this late Plains Basin was characterized by a non-rimmed platform, non-rimmed shelf, right? And you can see here, we're very lucky to see the transition from the inner platform, and then you go to the outer platform here, and you can really nicely see the shape here of this form. And I will come back to that later when we talk a bit about relative sea level change, right? But all in all, what we can say is that during the Plains Basin, we had an oligotrophic carbonate factory. So a very healthy, let's call it that, healthy carbonate factory, and also very productive here. That's a picture from the Tola Gorge. And here is the Sinemurian Plains Basin boundary is approximately around here. And you can see all these carbonates here, which form more than 500 meters of shallow water carbonates, are Plains Basin carbonates. So the very productive carbonate factory. And once you hit the Plains Basin Toarcian boundary, everything changed dramatically. So you can see here in this landscape how you switch from this Plains Basin, so the Aganan formation, you have this big geomorphological break here, which represents actually the switch from this carbonate factory, healthy carbonate factory, into something that is dominated by marls, and where carbonate production is actually impeded, right? And if we look very closely here at the boundary, we can even see that the topmost surface of the Plains Basin is actually represented by this ferromanganiferous crust. Sometimes it's a bit phosphatic. And we know from biostratigraphy as well that almost the entire early Toarcian is actually missing in that crust. And further east in Morocco as well, this very nice study on the Jebel Buddha here, you can also see here very nicely preserved isolated carbonate platform in the middle of the high atlas. You can see the blue here is the Plains Basin, and you can see then how the Toarcian and then the Arlenian deep water deposits are overlapping onto it. And so basically there was a big time here of hiatus and no deposition at all, right? And this Neritic carbonate factory crisis at the Plains Basin Toarcian boundary can as well be very nicely seen in deep water deposits in the basin. And basically here, when you go from the left to the right, you can see here on the left this very nice hemipelagic limestone marl alternation that all of a sudden stops net directly, and then there is almost no carbonate at all, but just a very clay-rich, silt-rich deposits of the Toarcian, right? And the reason for it is that at that time, there was a very poor, very, very feeble pelagic carbonate production during the Jurassic. So all the carbonates you can find in deep water settings are actually exported from neritic environments. So as soon as the carbonate platform stops, there is basically no more export of carbonate into the basin. And hence the halt in the limestone alternation and then the transition directly to this more CC clastics, early Toarcian. And the reason, and also, no, not the reason, but what we can see as well here is that this stop in the carbonate production is also linked to, in the western part of the basin, to an influx of CDC clastic, large influx of CDC clastics with some large pebbles in that. And a change now, we can find a lot of wood fragments and stuff like that. So we know here that there was a big climatic change, and we went from, during the plains back, and from something that was dry into now something that is wet. And that has been nicely modeled here by Dera and Donadieu, where if you basically at that time where you increase the level of CO2 in the atmosphere, you can see this change in humidity, right, in moisture. And you can nicely see here that Morocco here is situated in this part where actually you expect the largest change in terms of runoff, right? So this is all very consistent. And so due to the collapse of the Neritic carbonate factory now and the influx of CC clastics, now what we have is a really beautiful wave-dominated CDC clastic shelf, actually, that is developing here. And it's represented here by the Tagodit formation. Here's the Plains-Back and Toarcian boundary here down there. And then you see this huge, I think it's around 150 meters of deposits that are wave-dominated CC clastics deposit. That's me here highlighted. And if I zoom into here, you can nicely see this nice turbiditic deposits here, and you have even deep water channels here. So some very nice things. And if you go further up into the stratigraphy, you go from this more clay or silt-dominated sequence, and then you're getting coarser and coarser. You start to see non-amalgamated hummocky cross stratification. And if you go further up, you start to have amalgamated hummocky cross stratification. And then you have this upper shore face, near shore deposits with a lot of cross beddings, a lot of tidal influence as well in that. And then further up, you can even find continental deposits, right? So we have a really beautiful example of wave-dominated CC clastic shelves, actually. And when we look at this beautiful outcrop here, you can even see how this CC clastic shelf is prograding. And if I enhance here the vertical with the vertical acceleration, you can see actually all the clinoforms and all this progradation of these CC clastics here that are going towards the northeast, actually. And so what we can see as well, we can see that in the central high Atlas, if you're more into this part of the high Atlas, or even further east, the Jebel Buddha is somewhere here, and the picture I was showing you first was here, is that the early Toarcian is often missing from there, basically. So there was no sediment able to record anything there. But if you go to the west here, that's the picture I've just shown you before, there you have a lot of CC clastics that are actually recording the very earliest Toarcian events, actually. And this is due to the fact that to have CC clastics in a basin, you need a lot of water to transport the CC clastics, but you need also to have mountain to be eroded to provide the CC clastic material. And that's what we have, actually. And we know that from apartheid fission track studies that have been done in Morocco quite extensively, is that in the eastern anti-atlas, there was actually probably no uplift at that time. So there was no mountain. So despite the fact that it was humid, there was no mountain, so no material that could be provided. But the central anti-atlas was actually uplifted at that time. And so probably that was then a lot of material coming in from this part and fitting in the sediments. And then throughout the Toarcian, we can see this CDC class, this wave of CDC clastics or material actually entering and filling up the deposits towards the northeast. But the halt in the carbonate production didn't last forever, very long. And very soon after the boundary, we can actually find, again, lithotids, a lot of lithotids. So here are some very beautiful lithiotid bouquets here. And as you can see, they're dark and stuff like that. And that's because they now develop in what is a organic matter-rich lagoon, actually. So these lithotids, they are as big as the Plains-Bacchian one, but now they really don't care about the fact that probably the water there was highly turbid as well. So that questions a bit our understanding of what lithotids really were before during the Plains-Bacchian, if they were really in symbiosis with photosynthetic organisms. And we have also corals in this that are living together with the lithotids. And you're looking at something very rare, actually. You're looking at early Toarcian corals that before that have never been described, actually. But now they don't form reefs. We haven't found any early Toarcian reefs. So now they seem to be more solitary and living together with the Liquits, actually, in the lagoon. So maybe that's a place where they did shelter, but we continue on looking for early Toarcian reefs, and maybe we'll find some any day. And also now this new carbonate factory is a bit different from the previous one in the sense that it's now a mixed CC-clastic carbonate factory. And now what we have in terms of carbonate production is it is dominated by OID production. So there is now a really complete change from the plains Basin, which was really dominated, if you take a gross budget, by carbonate mud, into now something that is dominated by grains, by OID grains, right? But that again didn't last long, and unfortunately, the Toarcian oceanic anoxic event, or the what did cause it, stroke again, so the Carufera stroke again, and then we lose again the carbonates and then we switch back to a CC-clastic shelf. Again, and one that is dominated by waves. And now it's the proper downfall of the Liquits. And after that, there are no more Liquits. So the Liquits have been extinct at the onset of the TOAE. But this one is a bit peculiar because we have seen that there is actually quite a lot of storm deposits actually associated with this CC-clastic shelf now. So we can have some very large Hammocki cross stratification. And if we look in the literature, actually, it turns out that the equivalent of the Toarcian oceanic anoxic event in shallow water environments is full actually of storm deposits. So we can see that from Morocco, in Portugal as well, or in France, in Bajocian. There is always this insight that there is a lot of storm deposit associated with the Toarcian oceanic anoxic event, also in Japan, for instance, in more recent publications. But in Morocco, we can track that. So as I said, we can really track this deposits from shallow water to deeper water. And what we can see is actually that this Toarcian, this TOAE, we can find Hammocki cross stratification further offshore, I mean, further deeper into the basin than what we would expect from what we have before or after. And so the only way to explain that is that we must have had a deepening of the storm wave waves. So that means that we must have an intensification of the storm intensity. And so if we take all of that together and we put all these facts together, and plus the fact that the paleo latitude of the high Atlas at that time was 18 degrees, we can rule out winter storms as a driving mechanism behind the formation of the tempest tide. And so we come to the conclusion that there must have had been a significant increase in hurricane intensity associated with the early Toarcian hypothermal event. And that is kind of a dire prediction, because that's something that is actually expected by climate model, that if you have warming, you should actually have more intense hurricanes. It is empirically, it's difficult to observe at the moment, but it's predicted that that should happen. And so from this study in Morocco, I would really strongly advise you not to buy a real estate in Florida, for instance, at the moment, because it's really not a good place, I think, for that. But once more, the carbonate factor is quite resilient, and it came back relatively fast after the onset of the perturbation. And it came back same as before, as an O bioclastic ramp. So we have very nice oolitic deposits, very thick O bioclastic deposits, a lot with crinoids and sponge and sea urchin spicules and stuff like that. And we know as well that this carbonate factory did actually resume during the Toarcian oceanic anoxic event. So in the deep water in England or in France or stuff like that, there was a lot of anoxia and things like that. But at the very same time in Morocco, carbonate started to kick in again. And so we have actually here, we have the TOAE, and we already relatively soon after the onset of the TOAE, so which is characterized by this negative carbon isotope excursion, we have the we have large orbital shoals here. So showing that carbonate was already being produced during the TOAE, but what is relatively peculiar is that the ones relatively to the base are very small OIDs with most of the time only just one layer of coating around, and then they increase in size and in the numbers of coating around. So I'll talk a bit about that just in a few minutes. And relatively surprisingly as well, we see as well that now we have again, coral reefs. We have observed these very large coral reefs that are reoccurring really just after the end of the TOE. And some of these reefs actually can be 10 meters thick and some 50, 100 meters wide. So they're with huge corals in them. So clearly the TOE, if you go in basinal setting in England, it looks spectacular. It looks with a lot of organic matter, but it's really just the onset, at least for Neritic carbonate factory. That is very important. After that, the carbonate factory recovers very rapidly. And so if we summarize that, what time is it? Plenty of time. So if we summarize that, and I put that against what we can see here from the Mokras borehole in the UK. We see in the Mokras borehole, we can see using mercury actually tracer, we can see that there are two pulses here of volcanic activity, right? Coinciding with the Plains-Back and Toarcian boundary and the onset of the TOE. And those are exactly at the same time as we're losing the carbonate factory. So clearly we can make a very strong argument about a link between this change in the carbonate factory and global environmental change, right? And the driver, which is global, large Indus province volcans, the Karufera volcanism. If you look at osmioisotopes here, you can also see that there is a global increase of continental weathering, and that's also clearly something that we see here in Morocco with these two pulse of CC clastics influx, right, in the central high atlas, right? So the lithiotid fauna, as I said, disappear at the onset of the TOE. And what is most striking in Morocco is actually this switch from heterozoan dominated carbonate factory in the Plains-Bacchian. And then after that, into a heterozoan dominated type of carbonate factory. So now the question, now that we know that there is this link with global environmental change, the question is actually, but what is actually driving this change in carbonate production, right? And there are a lot of factors that you could think of, and some of you are listed here, and you can have a look at Krenke et al. 2020 for a review on that. And here are some of the 5 here most common ones that are talked about in the literature, right? And the question is, are we able to disentangle which one could be responsible for each of the 2 Neritic carbonate factory crises? I think we can from Morocco, and I'll try to show you why. The first thing is when we look at the Plains-Back and Toarcian boundary here, and we come back actually to the deeper water setting, it's very, very informative. During the Plains-Bacchian, you have this densely packed limestone marl alternation, so a lot of limestone and few very smaller marl interbeds. Here is the Plains-Back and Toarcian boundary dated by ammonites, no problem. And you can see from that here that all of a sudden you have an increase in the spacing in terms of the marl interval, right? And there is also a drop in the carbonate content in the limestone. And so we can actually infer from that there is a diminution of the production of carbonate. So the carbonates are starting to be, the carbonate production starts to be weakened. And so there is less export into the basin, right? And that coincides with the first arrival of the CC clastics, right? So we can think that this here, the start here, is really linked to the consequence of the enhanced hydrological cycle that is itself linked to the temperature rise, right? So we have enhanced continental weathering, so we bring also more nutrient, and that has been observed by phosphorus content, right? That you can measure in these deeper water settings. And so we switch already there from a healthy, let's say healthy photozoan carbonate factory into something that already starts to be less healthy. And we can actually we can see in the very last bed in shallow water, actually they are full of sea urchins, right? Which goes very well along with it, right? And this is also what Blomeyer and Reimer have called the drowning phase census stricture. So this switch, so this in between, right? But then we also know that because we still have some limestone beds, that it was still producing carbonate. So that is not what has caused the shutdown of the carbonate factory. The shutdown of the carbonate factory is here. So what's the consequence? And here we really think that sea level has a big role to play here. And here I bring you back to this really beautiful Jebel Buddha here, transect here, where you can see here this shallow water, inner part of the platform, the late plains Bajocian here, dominated by these lithotids, and then how this transitions into the deeper water. So here you have deeper water settings, and a few hundred meters later, you have shallow limestone alternations actually. So you can really nicely see how this transitions into that. And if that's another point of view here, so you can see here the shallow platform deposits here, and here you start to see this transition from the shallow to the deep with the limestone alternation. Here are some few coral reefs here inside. And here is the last bed of the carbonates. And on top here is this tagudite formation here. So that's this siliciclastic, wave-dominated siliciclastic shelf deposit. And if you look at it, you see that it pinches out towards here. And then if you look on top of it, you then see later on early Toarcian, but later on deposits that are onlapping on top of it here, and they onlap. Here starts the TOE here, and you can see all these deposits onlapping into it. And so if we do a lot of serial log here into this here, that's a very tedious work that François-Nicolas has done during his PhD actually, you can nicely figure out that this wave-dominated siliciclastic shelf is actually a low-stand system tract. So the carbonate factory crisis is actually associated with a relative sea level drop. And this relative sea level drop, because we know we have terrestrial deposits here, and here we know here in white below here is the shallow marine, plains Bajocian shallow marine deposits. We can actually measure here, and from a geometrical point of view, say that we have at least something like 40 to 50 meters of sea level drop that is coeval to the first Neritic carbonate crisis. So we think that this is actually the coup de grace that was given on already weakened Neritic carbonate factory that was due to climate-driven eutrophication. So that's what we think is the responsible for the first carbonate factory crisis, right? The one that is associated with the Toarcian oceanic anoxic event is a bit different. We think there are different drivers here. First, what we have to know is that this Toarcian OAE is actually characterized by a huge warming event, right? That you can see here with this TEX 86 here proxy here that shows this very big excursion, so that you can relate to a big warming event. So that could have contributed as well. We could have an overeating of the Neritic carbonate factory, as first of all. So then also with the storm intensity, that could have also weakened any buildup, right, due to increased hurricane activity. So, or prevented carbonate to accumulate there as well. So that's also possible. And if we look at sea level fluctuation at that time, it's actually the opposite than from the plains Bajocian Toarcian boundary. There we can also see a very large sea level drop of 50 meters, that with this beautiful incised valley here that you can see incising here. So here's a close-up, so you can see a 50-meter sea level drop. You see that this is a multi-story incised valley, so there is a lot of different fills. So here you have shore face kind of infills, and then you can see here on top that's probably there was a tidal channel. And if you look closely, I invite you to look at the paper where you can more zoom out. You can see actually lateral accretion package. In that, if you go on the side here, you can actually see some, what is probably some terraces deposits, so terraces that were left off during the forced regression. So beautiful example here, but that incision predates the TOE, and actually the Toarcian oceanic anoxic event coincide with a huge sea level rise actually. And if we start from the incised valley field, right, from the sea level drop that is there of 50 meters, and then at the top of the TOE, we have offshore deposits as well in this place. So we could infer something like 100 meters of sea level fluctuation from the onset of the TOE or a bit earlier until the end. So clearly the Toarcian oceanic anoxic event and the carbonate factory crisis associated with it are inscribed within a large relative sea level rise, right, rather than a sea level drop. So that's different as well. And there is also something that we have for the TOE that we don't really have, or not as clearly, I have to say, for the plains-pack and Toarcian boundary, is this large negative carbon isotope excursion here that has been linked to a huge influx of 13C depleted carbon, maybe linked to methane hydrates or other kinds of thing, right? But it was linked probably to a very large increase in the PCO2 level in the atmosphere, and the evil sister of that is actually ocean acidification, right? That you can get from it. We don't have clear evidence for that in Morocco, I have to say, but Rowan and together with her student Nick Etenge and Ettinger, I don't know how he wants it to be pronounced, and other co-authors went to the Adriatic platform, right? And they did find actually associated with the onset of the TOE, this very large erosive surface where they couldn't really observe any evidence for subaqueous exposure. And so they postulate that this must have been a subaqueous dissolution that you can then relate to an ocean acidification event, for instance. And this ocean acidification was also postulated earlier by Trecali et al., for instance. Here, based on the fact that what you observe here, so these wiggles here, those are lithotids, right? And then you observe this change in the Neritic carbonate factor is similar than in Morocco, where you go from a mud-dominated lithotid-rich type of carbonate into ooids, right? And these ooids, actually, they were postulating that those are the results of the ocean acidification, not directly the ocean acidification, but rather the overshoots that come after that, because ocean acidifications are actually associated with an overshoot of carbonate production after. And we have the same in Morocco. So that well possible. And we have also observed these very tiny ooids at the base with just one layer of coating. So that might as well still signify that we are in some kind of acidic or more acidic, not acidic, but more acidic waters, right, which was preventing carbonate production, right? And recently there was also this very nice paper from Müller et al. In geology, right, showing that clearly the TOE is indeed associated with this drop in seawater pH, right? So it seems that the TOE, really the ocean acidification event, is gaining more and more strength actually as the main explanation for the carbonate factory demise, right? So to conclude, I just want to highlight that this Neritic carbonate factory demise during the early Toarcian is a global phenomenon. Quite often you can only see one demise event because almost the entire early Toarcian is just completely condensed or missing or whatever. So it's really difficult to see anything. But in Morocco, because we have this high subsidence rate, this high sedimentation rate, we record actually more, and there we can see two distinct collapse phases. They coincide with the plains-pack and Toarcian boundary and the TOE event, and they are separated by a partial recovery interval actually, and that's something also a bit new here. So they are in phase with global environmental perturbation, and they clearly, I mean, we think they're paced by a recurring eruption of the Karufera large Indus province. Contrary to deeper marine environments, from a shallow marine point of view, it's actually the plains-pack and Toarcian boundary event that is the main event. It's not the TOE. The TOE, it's just a little blip into it. And if there was not this large negative carbon isotope excursion, you would have difficulties in seeing it actually, because it's just a relatively smaller interval of CC clastics input within the already ooid types of carbonate platform, right? And we think there are different causes at the origin of the two demise. For the P2 event, seawater eutrophication followed by sea level drop. And for the TOE, most likely ocean acidification concomitant to facies rise, but then we have also overeating could also have accounted for it and other things like that. On a positive side, we can also see that there is a Neritic carbonate factor is relatively resilient though, and so it quickly recovers, at least in the central high Atlas spacing. So it's a positive note, and that's so let us saying that if we stop perturbing the environment, we are likely to see the carbonate factory kicking it very rapidly, actually. And with that, I leave you with this nice picture of Liquits from the early plains back in here. And I'm happy to take any questions.
Stefan, thank you very much for walking us through late to early Jurassic in shallow water carbonates. And yes, dear audience, dear viewers, the chat is right now ready for questions. Yes, please also make sure that you're letting us know where you're watching us from. And Stefan, there is a first question for you from Emile, watching from France. Hi, everyone. Around the beginning of the talk, there was a little graph about the changes in the carbon cycle. What parameters were used to make it? Thank you very much for the very good talk.
Thank you, Emil. So I suppose you want to say how do we infer this change in the carbon cycle? I mean, that is based on this carbon isotopes, actually. That you have this, here is the black curve here, you have this really large negative carbon isotope excursion that you can find in deep water setting, but you can find it also in continental settings. So it's clearly a change in the, so it was linked to a rush of 13C depleted carbon into the atmosphere ocean system. And so to have that, you have to have a supplementary source of carbon. So that was the Carufera Larginus province, and probably the destabilization of methane hydrates either in the ocean or in the polar circle that have contributed to it. So that's how it is inferred primarily. And then there is also some evidence from stomatal index that PCO2 have changed quite a lot at that time.
Waiting for more questions from the audience. I think I can ask my one. Stefan, so you mentioned that, you mentioned how the processes which are affecting carbonate platforms are interrelated. So for example, the increased hydrological cycle is happening partly also because of the warming. And then you mentioned that the carbonate platform demise, the first one that happened basically because of the sea level drop, like 40 to 50 meters. How do you drop the sea level?
Oh, that's, ooh. Now you are opening the Pandora box, Ola, you know. Okay. That's a good question. I mean, we know from, there are a lot of evidence to show that, contrary to the common belief that the Mesozoic was warm time, at least for the early Jurassic, and now there are also some very good evidence from the, some undisputable evidence from the early Cretaceous, we suspect that there were some ice at the pole in that. And so we also know that the late plains backing is characterized by very cold conditions. There is plenty of evidence for that. And also the PCO2 level at that time, if I remember well, was around, that's a paper from McElwain et al., around 500 ppm or something like that. So in the Jurassic, 500 ppm is not a lot because the sun, right? The sun was less active. So the energy received from the sun was less active. And if you model that with 500 ppm, you are actually making ice caps, right? Now, it's true that we have not so far, although there are some paper on the way, direct evidence for ice in the early Jurassic, but there is plenty of evidence, of indirect evidence, and out of those, the sea level fluctuations are very important as well. And so we think that's, and this is also, this kind of makes actually this early Jurassic somehow a good analog for what is going on today, because we switch from glacial to non-glacial, things like that. So we actually in conditions, boundary conditions that are a bit more similar than what we have today, than, for example, the example from the PETM or the Cenomanian Turonian oceanic and Arctic events, where there it's more complicated to think that there was some ice at that time, but that is also disputed.
All right, thank you. I could throw a little bit more on that, but there are more questions and more praise for you. So Danielle from Vienna, right? Thanks, Stefan. Fabulous talk and beautiful fieldwork images, as expected. Wish I was in Morocco rather than in rainy Austria at the moment. So
I wish I would be in Vienna next week for EVU.
yes, I wish I would be in Vienna next week too.
Thanks, Daniel, for the comment anyway.
But also, I think that rainy Vienna is not such a bad place. That's true. Even if I also miss Morocco. All right. Our Valentine from Oslo. Excellent talk, Stefan. Very, very interesting. How much deeper did the storm wave base did get during the period of intensified storms? I'm sorry, I'm laughing because I remember these discussions very well.
Well, Valentine, I don't know. Unfortunately, we don't have any clear geometrical indication where we could read that directly from the outcrop. François Nicolas has submitted. He wasn't unfortunately successful now, but has submitted some proposal to work more specifically on that and some very highly detailed study on that. So I hope he will be able to do it and answer your question, but I can unfortunately not answer. When we did publish this paper, we were also asked by the reviewer if we could say something about the frequency of the storm. And we could have written something, right? Because we could have seen, but knowing the sedimentary record, I mean, that also would be kind of a very gross statement to affirm, and we prefer to stay on the more conservative side and not talk about that. But yeah.
Okay. Emanuela Mattioli, I believe, says, very nice talk. Thanks, Stefan.
Thanks, Emanuela.
The next question is from Joao from Holland. Hello, Stefan. Thank you for the interesting talk. How long is the interval of deepened storm wave base? Just the Toarcian oceanic event?
Joao, thanks for the question. Wait a minute. I'm trying to go back to this slide so it will be easier. Where is it? If we go here, this kind of brownish color shows the storm beds here that we have within the theory, right? And you can see that in Morocco, we mostly have it during the negative carbon isotope excursion and the onset of the plateau. But in Rabakar, they have storm beds higher up, right? So now here, the difficulty is to determine exactly, right? Because we have storm before and after. Here, the point was that this storm, this interval where we can see storm is actually getting deeper during during the theory. And it's actually, from Morocco, we can say that it's getting deeper, but during the onset of the negative carbon isotope excursion.
Okay, the next question
you have in terms of time, if you want to put a number, then you have to refer to cyclostratigraphic study, which unfortunately, as you must know, are kind of divergent in some parts. So I cannot give a definitive answer.
Okay, so the next question is from Amelia, I believe, in Erlangen. Stefan, thank you for a fantastic talk. Your field work is truly impressive. Do you think there is any component of phase shift in the photozoan to heterozoan transition? For example, whether they represent parts of a similar factory coexisting at different depths, given the big change in the relative sea level?
Thanks, Emilia, for the question. You should also thank François Nicolas, who did a lot of the field work. So he's behind a lot of this data collection. No, actually, no. And that's the great thing about having this lateral continuity where you can track things from shallow water to deep water. We can actually see, indeed, during the Plinsparkian, when we have this photozoan dominated, and that's why I use the term dominated. this photozoan dominated carbonate. The photozoan part of it was indeed in the shallow water part, where you in the U40 part, right? And then we can see then when we transition into the deeper part, then we have indeed heterotrophic or reworked phototrophic organism, but that we can see, right? But then when we enter after in the Toarcian, we don't have clear evidence for phototrophic organisms or significant production of carbonate from phototrophic organism. Again, we have lithotids and we have corals, but clearly we have some real doubt that the lithotids and the corals were actually in symbiosis with photosynthetic organism at that time, because they were, I mean, they were both living in some very muddy lagoon and stuff like that. So, and the reefs and the coral reefs are in the lower shore, I mean, shore face of upper offshore transition. So no, that's the, it's indeed always a good question. If you just have a 1D, a column section, and you see a change from photozoan to heterozoan, you're not sure if it's due to a genuine switch in the environmental conditions, right? Colder, more nutrient, or if it's just a relative change in sea levels or in water depths, right? But here in Morocco, because we have this transect, we can clearly say that this is due to environmental change in terms of nutrient level, temperature, and stuff like that.
All right, Crispin from Leeds University is asking why use the term Toarcian anoxic event when there is no evidence for anoxia in Morocco or indeed many other sections. The Jenkins event is better term as it encompasses many the events in the early Toarcian. Also, a paper by Lee et al. In Chemical Geology in Press questions ocean acidification in the early Toarcian based on calcium and strontium isotopes in carbonate from Peniche section.
Yes, I'm aware of this study. I was a reviewer of it, so that's not a surprise. But so first question is, yes, you are right. I'm a bit reluctant to call it the Jenkins event because I think it's Hugh Jenkins who told me once that it was maybe not so, you know, because kind of, or was it Helmy? But I'm not sure. But you know, naming an event after someone that is still alive, he said it was a bit awkward. But you are entirely right with that. There is no evidence whatsoever for anoxia in Morocco, and in a lot of the world there was actually no anoxia. So it's not an oceanic anoxic event since the ones that are in the Cretaceous. It was more linked to regional restrictions and things like that. I fully agree with you on that. But yeah, I have TOE in my head, and but I should try to name it the Jenkins event. And yeah, the Lee et al. Paper, yes. I mean, again, I am also not saying for sure it's ocean acidification, right? Clearly, as we can see from the Prince-Back and Toarcian boundary, even you don't necessarily need an ocean acidification to have this big impact on the Neritic shallow, on the Neritic carbonate factor, right? Yeah, I think more research needs to be done. Yeah, I'm also not sure I can entirely follow the conclusion of Lee et al. and on that, right? And so it's also basically, I think, if I remember well, their delta 40 calcium, for instance, curve do not show any change. If I'm not entirely sure, excuse me if that is not true, but I think doesn't show any change at the Prince-Back and Toarcian boundary, which I find very awkward, seeing that it's a global demise of Neritic carbonate factory, which was actually the main carbonate producing, I mean, the main carbonate producer. So I have difficulties in understanding how that doesn't show up at all in the carbon isotope record, for instance. So in the calcium isotope record, there you go. I find a good word. But yeah, it's still open question.
So Emanuela is asking her question right now. she gave you her praise before. Right now comes the question. How do you explain an acidification model that calcareous nanofossil fluxes are the highest in the polymorphism zone and that very delicate coccoliths, solution susceptible, are recorded in the Toarcian ocean anoxic interval.
I don't explain it, Emanuela. Yeah, you're right. I mean, it could be it's not compatible. I mean, though you said in the polymorphom zone, I mean, that should be the prior to the ocean acidification events that prior to the onset of the TOE. Now, where exactly have you seen this very delicate coccolith within the TOE? Is it right at the onset? Because then again, very soon after the onset of the TOE, Neritic carbonate factory resumes. So then you might already be in the overshoot situation, right? If in the case of an ocean acidification, if it's true, I cannot answer to you, but I would be happy to talk with you about that and see if we can tell more about it.
And I didn't read it quite till the end. Emanuela was or is watching us from Lyon. The next question is coming from Scotland, from Ian. Nice presentation. Reminds me how great the Morocco sections are. Wondering if you have also considered the role of Central to North Atlantic rifting in controlling sea level or oceanic circulation patterns.
No. No, I haven't. Might be possible. Although, right, the sea level fluctuation I'm talking about are occurring on timescales that are less than 1 million years or something like that. So I'm not sure that central, I mean, the North Atlantic rifting would, on this type of timescale, have an impact actually. So, and ocean circulation patterns, yeah, that's something we would like to look at as well, and especially the role of this connection, the opening of the connection between the Tethys and the Pacific. There are some people suggesting that it already happens in the Sinemurian, if I remember well. So there is also papers that are dealing about ocean currents coming from the boreal rim into that. So that's also something we should look at. Yeah, indeed.
All right. The next question is from Maciej from Warsaw. Those organisms were in situ or were taken from their environment during storms. We have some mixed fauna from deep and shallow water.
Most of the organisms I'm talking about are indeed a bit reworked, not necessarily by storms, right? But the reefs and things like that are in situ, right? And indeed, if you go into the deeper water environment, you can find often quite a lot of reworked organisms, right? Yes. But yeah, don't know if I have answered your question or if you had a more specific question or in mind or.
So I would say, Maciej, if you have a more specific question, please type it in the chat.
So, I mean, the mixed fauna from deep and shallow water. If yes, very rarely. I think it's I'm not sure in the deep water having seen corals, clear coral fragments or oids or something like that. It's not some. I mean, there is some lateral transport, but it's not kind of a big mess, and you're not able to distinguish things. So it's relatively, you can relatively distinguish depositional environments within that.
Okay, I see that right now Maciej has just wrote that yes, this was what he meant in one layer. The next question, wait here. Stefan, thanks for the very detailed talk. You showed that the Plansbachian torsion drawing was a series of events, drawing zone. Which process or series of processes related to this zone, as it is not a single event? John from Amsterdam, yes.
Hi, John. So which process or series of processes relates to this zone? I'm not sure I fully understand your question, John. But the we see clearly this change from the Pliens Bakken, and then so we have this photozone dominated carbonate factory, and then towards the top we have something that is more towards heterozone, with, as I showed on the pictures, with more sea urchins and things like that, and we can see this diminution of the carbonate production as well in the deep water record, right? We can infer that from it. And then we have this really big stop switch there, which is dated from the very earliest Toarcian, right? And if you refer to Jebel Buddha as well, I think that is on top. There are the very same ammonites from the Tenuicostatum zone. I mean, on the top of what you have called the drowning succession, actually. So I think what you have called in your paper, the drowning succession, is really this change from this healthy photozone carbonate factory in the Pliens Bakken, and then this very earliest Toarcian, you have this what you call the drowning phase. So this change on that, and then the sedimentary record stops on the Jebel Buddha, and then you have only in deep water settings, but I think, I'm not sure if it's well dated, so I have to check again, but I think it's then you have the Toarcian marls, but these Toarcian marls, at least in Aitatman, for instance, so it's a bit further west, starts to be dated from the early to middle Toarcian transition. So there is a big hiatus on top of that, and I think you have it's the same in the Jebel Buddha section. But then further west, then there is another type of carbonate factory that comes in, and I think that is actually not recorded in the Jebel Buddha actually. And I suppose the reason for it is that on the west, due to the CC clastics influx, there was then, once the conditions were favorable again for carbonate production, there was then some areas where shallow water carbonate could reinstall for there. But I'm not exactly entirely sure why does the carbonate factory only, starts to recover only in the western side and not in the eastern side.
So a comment from John to that is, Stefan, thanks for the discussion. So it's not a single event, right? Great talk.
Yeah, it's not a single event. It is two separated events. Yeah. Yes. Yeah, and I think Philippe Leonid also did show that he had this very nice section. Was it occurrence section? I don't. Where you have these two drowning and conformity separated by a little bit of carbonate there that were related as well to these two events. But unfortunately, in a lot of places, actually, the whole early Toarcian is completely missing. So there is no record basically of this event.
Next question is from Simona from Palermo. Thanks for your interesting presentation. Have you found paleosols in Pliensbachian carbonates?
Yes, a lot.
Okay.
You have a follow-up question? Yes, yeah, a lot. I mean, there is a lot of paleosol. We have calcrete and stuff like that, and I remember frantically sampling them with the idea of using this to make a PCO2 record, and then I realized that because it's in carbonates setting, it will not do anything because it's not possible. I mean, you need to have it in a calcrete in CC clastic setting to be able to do that. But yeah, there is plenty. There is this Aganan section with the lithotids. Actually, you have small parasequences here. I would refer you to the nice paper of Wilmsen and Neuweiler, 2008 in sedimentology. They have described that very nicely, and then you can see. I mean, there is a lot.
All right. So just another comment, I would say, from Crispin. Stefan, I should also have said that your work is really fantastic in its details and effort. I wish we had such a good exposure in Cleveland Basin.
Thank you, Crispin. Very nice. Thanks.
Yeah, I admit that the Moroccan exposures are really exceptional. So I think, I mean, there are a lot of praises and a lot of thanks for you, Stefan, from our viewers. And I think that with this, we can just wrap up today's webinar. Thank you everyone for joining us tonight, and thank you for the great questions and comments. Next seminar is, well, the same time, the same place next week at 4 o'clock, and it will be given by Amanda Ohlad. She will be talking about investigating heterogeneous geochemistry of brines and sediments from the Salar de la Mara, a case study from polyextreme environment. And yes, we hope to see you all next week. Thank you very much.